So our next speaker is Felix Strieth-Kalthoff. Felix is an assistant professor of digital chemistry at the University of Wuppertal. Before his current position, he did his PhD in organic chemistry at the University of Munster with Professor Frank Glorious and a postdoc in chemistry and computer science at the University of Toronto with Olan Ashbroguzik. And Felix's talk today is on machine learning hits the lab, experiment planning with Bayesian copilots. Felix, the floor is yours. Please present when you are ready.
Okay, awesome. Yeah, thank you, John. Thank you so much for the intro, and also thanks to AI-Chemie for the invite to speak here today. Yeah, as John said, I'm an assistant professor of digital chemistry, whatever that means. But yeah, my trajectory has for a very long time not been digital at all. In fact, as John said, I have been trained as a synthetic organic chemist. I've spent my PhD in a hardcore synthetic organic chemistry lab where I was kind of the odd one out, like the one kind of person that was a bit interested in computational tools in a lab full of hardcore synthetic chemists. But yeah, with that interest, I moved on to my postdoc at the University of Toronto, where things were exactly the opposite. Well, I was still the odd one out, but this time the other way around. This time I was the one experimental person in a lab full of computer scientists and computational chemists. But really what I've taken away from that is that there's incredibly much to learn and incredibly much to explore if we actually start talking at these interfaces. And that's why I'm also very, very happy to speak at an initiative like AI-Chemie today, and because here we have an audience that is clearly interested in this intersection. And to kick off my talk for today, actually what I want to talk about is a problem that, or is a question that I have been asking myself pretty much since I was a PhD student, since I was standing in a synthetic organic chemistry lab and spending a lot of time on optimizing reaction conditions, finding the right catalysts. And the question is simple, but fundamental. How do we actually decide which experiment we're doing next? And I mean, in principle, we as scientists, we should know the answer to this, because the scientific method provides us with a very, very clear recipe of how to do this. We observe something interesting, we form a hypothesis on how to explain these observations, and then our purpose of designing experiments is to come up with new experiments to either verify or, worst case, falsify this hypothesis. And then we go on, rinse and repeat, observe new things, form new hypotheses, design new experiments until we arrive at a satisfactory outcome or a satisfactory conclusion. Easy enough. Well, we're also all scientists, so we all know that, yeah, this is everything but easy, because observations that we work with and observations and data that we deal with usually deals with very many dimensions and nonlinear effects, which, yeah, obviously makes it hard to design hypotheses ourselves as humans. I mean, my brain maxes out at thinking about maybe 3 dimensions on a good day. So yeah, with all the experimental data that we are facing in a synthetic chemistry lab, there's no way of doing that. At the same time comes an additional issue, and that is the fact that in a lab, we're often dealing with phenomena that we cannot or only superficially simulate. So the question is, what do we do in these cases? And of course, these slides were kind of made for a more chemistry audience. So to all of you, they shout, can we support all of that with machine learning? And can we decide on, or can we start developing machine learning algorithms that can help us in the process of hypothesis generation and ideally in the process of planning experiments so that we arrive at actual lab conclusions at a minimum number of experiments? And I mean, if we start dreaming, and many people started dreaming about that, effectively these days, every software has to be AI powered. We need AI copilots in literally every piece of software that we're using, that we're developing, that we're buying these days. It feels like AI powered in commercials has become the new chemistry free. So the question is, like, if these AI pilots are everywhere and they're undoubtedly useful in many scenarios, how far away are we from from developing copilots, tools that will actually help us to facilitate decisions in a chemistry lab, and that will help us to make better decisions within a chemistry group. Well, enough science fiction for now. Back to reality is that I think we're all aware that this is still years, probably decades down the road, like a general purpose tool that will just look at whatever problem we have and give us meaningful suggestions. That's probably not going to happen soon. And the question is why? Well, all of those copilots that are useful these days are built on data that is either language or that is images. And we have tons of that data, and that's why we have good AI that can deal with that. Well, a bit simplified, but that's the idea behind it. The problem is chemistry is not language, and chemistry is not images. Chemistry is special, and by special I mean rather difficult to describe for AI. Why is that? Well, number one is the point that I already hinted at, because we just don't have as much data. The GPTs of the world have been trained on effectively what is the entire internet, and are now facing kind of issues in finding more data to build stronger and better models at. In the natural sciences and in chemistry in particular, we're far, far, far away from that. But that's only one part of the truth that makes chemistry different from language or images, and would probably be too easy to say, yeah, we can't build meaningful decision-making tools, AI tools for chemistry because we don't have the data. Well, yes, we don't have the data, that's true. But what we have instead is we have the laws of nature. Scientists have spent the last 200, 300, 400, and probably even way longer years to try to understand how nature works and how all the matter, all the environment around us functions. So even if we don't understand all the phenomena that we're trying to explore and research, we still have a big and a very good understanding of the general laws of nature that govern all the life around us. So we should use that rather than throw it away and try to learn everything from data. And then there's a second thing that makes chemistry special and very different from languages and images. And that's kind of some rather practical concerns. Number one is we have extremely large decision spaces. If we just think about the world of small molecules, and that's what I'm going to talk about in my talk today, we talk about decision spaces that are somewhere in the order of magnitude 10 to the 60, 10 to the 80, 10 to 100. That's way more words than there are there in any language, in any grammar. So like we have to kind of make decisions on a very, very large space with very, very limited data. That's kind of the hard part. And hard part number two is something that is very often ignored, is the fact that we can design a lot of things, and we can design a lot of molecules or materials or experiments. But from time to time, yeah, things in a lab just don't really work out that way. And sometimes a lab has its own ways of telling us, yeah, this experiment is not going to work. And I think what is absolutely crucial to develop meaningful prediction tools and meaningful assistance for a chemistry laboratory is to actually keep these factors in mind and actually include all our expert knowledge and all our experience as chemists into decision-making models. And that is effectively what the mission of my research is, or my research group is, that has existed for about half a year right now. So our main mission effectively is to develop resource-efficient decision-making tools for the synthetic chemistry laboratory. So, and I on purpose say laboratory because my lab is clearly a hybrid computational experimental lab, and any tool that we're going to develop and any tool that will come out will be focused on actually streamlining workflows that we do in a synthetic chemistry laboratory. Well, that kind of has two inputs in there, or two components. Number one is we need to make the chemistry lab data ready. So what we need to develop is digital toolboxes and digital workflows that actually help us to generate more data and access the data that we generate in a synthetic chemistry lab in a better fashion. So what we're working on is automating lab routines, trying to develop interfaces for common lab equipment, and so on and so forth. And I'm going to show you two examples of that in a bit. And on the other hand, it's meaning we have to make machine learning chemistry ready. So we have to include all the chemical phenomena, the chemical knowledge, the chemical intuition from time to time that we have into a computer readable fashion so that we can actually use it for machine learning. So I think like making or like building meaningful, useful tools requires both making chemistry a bit more machine learning ready and making machine learning a bit more chemistry ready. And actually the left-hand part is something that has been bothering me for a couple of years now. Whenever we work in a synthetic organic chemistry laboratory or in a synthetic chemistry or a chemistry lab in general, we're working with a lot of instrumentation, a lot of things that are inherently not very well suited for getting data out and for getting information out that we want, or for controlling them in the way that we want them. And that's why in the past years, like both during my postdoc and that has continued on to these days, what we're effectively working on is Pythonizing the chemistry lab and trying to develop Pythonic interfaces for as many of the tools that we are encountering and working with in a synthetic chemistry lab. These days, many of the commercially available software tools still don't come with good usable APIs, and the more we've been talking to other groups and to other people that work in the same field, they also say, yeah, we developed this hack, we developed that hack for this instrument. And rather than having 5 groups reinventing the wheel all the time, what we've started to do is just making our hacks usable for others, publishing them. For the ChemSpeed robotic platforms, we have published an open source Python controller called ChemSpeed earlier this year. We're also in the process of releasing a Python version for an automated synthesis robot, and my lab is very actively involved in developing open source solutions, for example, for chromatography, for HPLC and GCMS systems. That's kind of the part of making chemistry labs more data ready. But what I find almost more interesting is the other side of research. That is the side of where we start with chemistry problems in hand and try to develop machine learning solution and figure out the machine learning solution to that problem. Either the cheminformatics or actually the machine learning methodology solution is just not there. And also my lab has been involved in a bunch of those initiatives. Don't want to go into too much detail here because yeah, I rather want to focus on the longer story for the rest of my talk. But for example, what we've been working on very actively is Bayesian optimization or Bayesian decision making with hierarchical composite objectives. So how do we actually do multi-objective optimization if we have a hierarchy of objectives? And ideally, we want this hierarchy to be differentiable, to be flexible, so on and so forth. There was surprisingly not that much out there that we would have hoped for. So that's something that we're about to publish. What we've been involved in is making Gaussian process models ready for molecular structures. That's a work that was led by Ryan Reeds-Griffiths in Cambridge and at Meta back in the days, where we developed a bunch of different kernel representations for molecules and even up to proteins that can be effectively used in Gaussian processes. The library called Gauche is by now like fully publicly available, and I think I've seen quite some use cases, which makes us very happy. Earlier this year, or like better last year, but it was published earlier this year, what we've started to develop is trying to do Bayesian optimization, where we try to leverage prior knowledge from large language models. So effectively trying to harness the fuzzy knowledge that a large language model has and use that more or less as a prior for more efficient decision-making in Bayesian optimization. That was together with Agostinos Christiadi at the Vector Institute in Toronto. And very recently, what we've been working on a lot is Bayesian optimization for generality. So Bayesian optimization to find conditions that are not like a very, very specific optimum, but rather optima that are readily transferable to other related problems. Okay. But that was pretty much a bit of a run through and kind of to give you an overview what we are working on these days and what my lab is working on these days. But for today's talk, I thought rather than giving you 3 minutes of this and 3 minutes of that and 3 minutes of that, and then not telling you anything overall, what I thought we'll do today is like a very brief overview of what we do and then dive deep into one research project that has a couple of all of those components in here. And that's what I want to do for the rest of my talk. I want to dive a bit into machine learning for accelerating molecular discovery. And molecular discovery, as I pointed out, is like one of those problems where we have this big issue of massive decision spaces. If we want to design a molecule with a specific function, well, the space of possible molecules that we can search through is, yeah, estimations vary because it's not exactly easy to come up with the right number, but for small molecules, whatever small means, we're roughly in an order of magnitude 10 to the 60 to 10 to the 100. So massive decision spaces. Just as a reference, all molecules that have been synthesized or not even synthesized, but characterized these days, could have also been isolated from nature, is roughly on the order of 10 to the 9. So we have a massive discrepancy here. So any machine learning model that we want to predict as new molecules should in principle operate on this 10 to the 60 to 10 to the 100 space. Problem is the synthetic organic chemist inside me, and as I said, I was trained as one. So that's like something that where the synthetic organic chemist inside me starts ringing all alarm bells. There's no way that we can synthesize all of these molecules with a reasonable effort. There's no way that we have a model that proposes us any molecule and then we make it, test it, feed it back. There's no way of doing that experimentally. So if we actually want to do realistic machine learning driven molecular discovery these days, and ideally do that in an iterative fashion so that the model learns from what we have predicted in previous rounds, we have to go a different approach, and that's the idea of virtual libraries. So instead of trying to master all kinds of reactions and all kinds of chemistry to synthesize all of these 10 to the 60 to 10 to the 100 molecules, what we do is instead we try to focus on just a subspace of that. And a subspace that has a defined form, for example, this very ugly looking shape here. And instead of mastering all chemistry to synthesize all kinds of molecules, we just focus on mastering some types of chemistry, namely the ones that we use to put these fragments together. And then with the right fragment library, combinatorics can play in our hand and actually give us access to a rather large and reasonably diverse virtual library of possible compounds that we know we can make by just mastering some types of coupling reactions to put these building blocks together. And just to give you an idea, this idea of virtual libraries is of course nothing that we invented, but that is very well known in modern drug discovery, for example. And there are commercial companies that sell these virtual libraries. And the largest virtual library that is currently commercially available, so where there's a startup or a company somewhere that tells you, from this library, we can make you any molecule on demand if you want it. The largest library has a size of 10 to the 11, 10 to the 12. So like larger than the number of molecules that are currently known and characterized these days. So yes, with virtual libraries, we sacrifice some of the possible small molecule space, but what we gain is rapid experimental access to all of those. And that was actually the strategy that we wanted to go for in this project. So now I told you we want to discover molecules, or we want to do it with a virtual library. What I haven't told you yet is which type of molecules we want to discover. And the project that I was working on back in my postdoc, where what this story is focusing on, is thin film organic laser emitters. And probably most of you have not heard about thin film organic laser emitters yet. In fact, up to 3 years ago, I hadn't heard about that either. Although time flies, so I should probably say 3.5 years by now. But yeah, back in those days, I didn't know anything about organic laser emitters either. But in a nutshell, the idea is that we embed such a molecule, such a conjugated organic molecule in an organic semiconductor thin film. And by charge injection, we populate the excited state. And if we do all of that in a cavity and achieve population inversion, then we can get laser-like emission from an organic molecule, which is envisioned to kind of induce a bit of a revolution in the field of lasers, similar to the way that organic LEDs have revolutionized the LED market. So color tunable, flexible devices cheap manufacturing. That's kind of the dream from organic lasers. The problem is, back in 2019, actually the first thin film electrically pumped organic laser was ever demonstrated by the team of Chiaya Adachi in Japan. And since then, Adachi's team has shown about maybe 10 emitters that can do this laser-like emission in thin film. So effectively, we don't really understand yet what molecular features and which features actually lead to laser-like emission. So what our goal here is, we need to find more and better molecules that actually fulfill these laser-like properties, so that have a narrow emission, fast emission, and high quantum yield of populating the excited state. And as I said earlier, like searching the entire space of 10 to the 60 to 10 to the 100 is maybe possible, but clearly unrealistic. So we went the exact same approach that I just highlighted on the previous slide. We went for all of that with a virtual library approach. So we started taking the parent scaffold from Chiaya, fragmenting it into molecular building blocks, namely this cap, bridge, core, bridge, cap, symmetric ABCBA structure. And by just checking which fragments here are commercially available, we ended up with a library of a couple of 100,000 molecules. Not quite 10 to the 9, not quite 10 to the 12, definitely not 10 to the 60, but a good feasible space of molecules that could potentially lead to good laser emitters. And as I said, for building these virtual libraries, we need to master the chemistry to actually couple those building blocks together. And in that case, the chemistry that we tried to master here was the iterative Suzuki chemistry that was pioneered by Marty Burke at the University of Illinois a couple of years ago. I think 28 was the first example. But effectively, what we do here, we do a standard Suzuki coupling between the cap and the bridge. We form this AB bond and then have this funky looking functional group in here, which effectively is a protected boronic acid, which we can then release so that we have another boronic acid and couple them with a symmetric bromo core bromo building block to build up these symmetric ABCBA pentamers. And if we just go to the catalogs of specialty commercial suppliers, we can get all of those building blocks or their direct precursors. We can buy them, and if we just enumerate whatever is cheaply commercially available or synthesizable in one step, we easily arrive at a library of like roughly 200K laser candidates. So a pretty solid pool to actually start deciding from. And now the workflow that we envisioned and the workflow that we wanted to build for actually searching this library of 200K candidates is relatively straightforward, and every one of us has probably seen multiple of those design, make, test cycles. So we have some kind of machine learning model, some kind of AI co-pilot, if we wish, that actually tells us which of those 200K molecules should we make. We actually synthesize them. We purify the reaction mixture. We measure the property of those molecules. So is it a bright emitter? Does it emit narrowly? Does it emit fast? And we use those properties to actually reinforce our decision making here to improve our candidates iteratively. And now the dream was, can we actually do all of that in an automated fashion, or in a fashion that's as automated as possible? And actually on this slide, I'm going to condense a lot of hard work from different people into just one slide to highlight, yes, we could. Effectively, what we started developing is like multiple platforms that can actually do this iterative Suzuki coupling. Took a lot of time. I don't want to bore you with experimental details. From there on, the crude reaction mixtures directly go into a chromatography mass spectrometry system for purification and analytics if the reaction worked or not. And from there on, the purified sample automatically goes into a spectrometer that measures absorption, emission, time-resolved emission to estimate the laser-like properties. And this proxy property, it's obviously not a thin film that we measure here, but it's a proxy for that, then goes back into the decision-making algorithm. And what we were able to achieve is to actually implement this into like a larger workflow where also the building blocks are automatically synthesized, molecules are synthesized, purified, properties are measured. And for some of the successful candidates, we then have options to scale up and actually test them in a thin film device. And well, the latter part was not quite automated yet. But yeah, what I kind of pointed towards already. This was a massive, massive team effort. And this slide is probably, of all slides I've ever presented in my life, the one that condenses the most hard work of many, many people into a single slide. And I'm very grateful to you that I've been part of that team that consisted of 5 labs all across the world, like Alain's lab, so my postdoc lab in Toronto, where especially Han and Martin, my colleagues, were involved. And the lab of Marty Berg, so the inventor of the iterative Suzuki chemistry at the University of Illinois in Urbana-Champaign, with Nick and Vandana involved. Then Jason Hines' lab in Vancouver, who were like really the grandmasters of synthesis on scale, so both building blocks and scale-up properties. Lee Cronin's lab in Glasgow, and then Chiaya Adachi's lab in Japan, who actually took care of the final device testing part. But yeah, as I said, I don't want to focus too much on the experimental details here today, but rather what I want to focus on is we have this pool of 200K laser molecules that we can potentially make. How do we actually do this decision making? And at the beginning, as I said, there was effectively not much known about organic lasers. 10 molecules known, maybe 20 molecules known, pretty much nothing known about structure-activity relationships. So what we started with is just statistical sampling from that space. So we did 500 experiments. We followed the classical Fisher design of experiment approach. We did a partial factorial design in our full combinatorial cap-bridge core space. We did those 500 experiments in an automated fashion also to test all our platforms. Yeah, and what we ended up with is that if we just statistically sample from that space, most lasers are bad. This is just the histogram of lasing performance, emission gain cross-section. So lasing proxy, and we see like in the region where we want to be, 2.5, 3, 3.5 to the minus 16 square centimeters. There's just no lasers in here. So yeah, we tried to augment this data with some of the knowledge that we had. So Chiaya's lasers and some of the molecules that we tested on the fly don't really change the picture. Like statistically sampling from this space doesn't really work, and what we need is some more advanced and some more informed decision making. The good thing is that in principle, the tools for that have been developed probably over the last century. Starting from like Fisher's seminal work on the design of experiments, that's probably like part of most scientific curricula these days. People have started developing like better and better approaches for such ideas of iterative experiment planning. Starting from Wald, who was like one of the pioneers of sequential analysis of statistical data, so planning experiment, getting the result out, and then sequentially designing on the next experiment. Over in the 1960s and 70s, the theoretical framework of Bayesian optimization and Bayesian decision making. The problem is like nobody had really cared about these approaches. Nobody had really cared about these Bayesian decision making tools up until beginning of the 2010s, when they became really, really popular in Bayesian optimization for hyperparameter tuning of complex neural networks. And that has really given a complete boost to the field of Bayesian decision making. It has made Bayesian optimization more or less the standard approach, like the default go-to strategy if we have iterative experimental design, if our experiments are expensive, and if our experiments are a black box. And effectively, that's the scenario that we're facing here. We want to do iterative experiments. We don't want to do 1,000 experiments first and then test what we do. But we want to do them one by one and kind of learn from what we've gone through. We want to minimize the number of experiments because every experiment takes time, takes resources, takes energy. And our experiments are effectively black boxes. So we can run them, but we don't really understand yet what's going on there. So Bayesian decision making should be directly kind of the way to go. And just as a brief overview of how that in general works, so we show our model some of the laser molecules that we've measured. Let's say in this very simple picture, we have those 4 data points. And then machine learning models or Bayesian models in general are very good at interpolation. So what they'll probably learn is lasing performance across this entire space looks something like that. And if we now ask these models, hey, where should we actually do pick the next data point, the next experiment to do, it will probably tell us of all these possible molecules that we have, go somewhere here, because here is where I predict the highest lasing performance to be. And that's actually where the Bayesian part comes in, because this is, of course, not enough. Because the model in this region of space here learns, okay, lasing performance is rather poor, even though it has never even seen a molecule in this domain of space. So what we actually need for effectively navigating this space is we don't only need the predictions, but we need the model's confidence in its predictions. Or in other words, what we need is probability distributions over our entire space. And if we have models like that, and the good thing is Bayesian theory provides us with a formal way of getting those uncertainty-aware models, the uncertainty prediction would probably look something like that, where it tells us, okay, here in this domain of space, I literally have no clue what lasing performance would actually look like. And the key for decision making is then to implicitly use a trade-off between, on the one hand, exploiting what we know and what the model have learned, so using the predictions, and exploring the domains where the model is completely uncertain, so using the uncertainties here. So theory looks great. What we now need is actually a model that can do this, and that can actually make these predictions. And we started trying developing something like that. And when we started off, we really faced like a major issue. So what we see here is just prediction accuracy, or like prediction performance in R square over multiple train test splits of the few training data points that we had. And effectively what we see is different molecular representations. Whatever we try in terms of the standard molecular representations that people would use for representing molecules in a computer-readable fashion, don't really give us any good predictive performance. Neither fingerprints, nor descriptors, nor even DFT computed descriptors on the individual building blocks give us any good predictive performance. In fact, none of them outcompetes a simple baseline, a simple one-hot encoding that doesn't even encode any structural information. All it contains is literally the information cap number 27, bridge number 33, and core number 127. Nothing more, no chemical information, and it just performs just as well as any of the more chemistry-informed descriptors. That's a bit of a bummer, but it kind of also tells us two important things. Number one is learning lasing performances for molecular structure only is a damn hard problem. And number two, it tells us lasing performance is nothing that is like a combination of all parts. So we can't describe a molecule just as the sum of its parts. But what we need is we just need to describe the molecule as a whole. But still, the prediction problem is quite difficult. And that's also very well seen in like these scatter plots here, where we put for all pairs of molecules that we observe experimentally, what we plot is the structural distance measured in fingerprint distance against the functional distance measured in the difference of their experimental lasing performance. And what we see is that we don't see anything. If we had a perfect structure activity mapping, meaning that similar molecules give similar performance, and that's kind of the basics of all QSAR approaches, then what we would put here, or what we would expect to see here, is a perfect diagonal, or a perfect linear correlation. The problem is we see everything but not a linear correlation. What really tells us, like, molecular structure alone, or structural similarity, is really not a good measure for getting an idea of what lasing performance is like. So in other words, the question is, how else? How else could we represent our molecules then? And that brings me back to a point that I tried to make earlier, which is the point that, yes, we have little data about the systems. But what we have is we have our physical knowledge. We have our knowledge about how, in general, lasing works. Even though we don't understand the exact physics of it and the exact mechanisms, we know that lasing has something to do with excited states. And we have some idea of understanding and describing excited states. And this is what we tried. So we tried to feed our knowledge, our information about excited states into the model. So we take the molecular structures, run through a simulation pipeline of sampling conformers, optimizing geometries, and computing some excited state properties. I don't want to go into too much detail, A, because it's not too relevant, B, because I'm definitely not the person that did all of that, but I want to shout out to Han, Chen, and Robert, who did all of that work and like fully automated this pipeline so that in principle for every molecular structure in about, say, 20 minutes to half an hour, we can actually get a vector of DFT properties. And if we try to represent our molecule with these DFT excited state properties, we actually for the first time start seeing some predictive performance that goes a bit above what the one-hot encoding does. Not very strong yet, but at least it kind of tells us, okay, we're somewhere on the right track here. But there's something more that these DFT computations allow us. They now allow us to get data from molecules on a scale of probably 15, 20, max 30 minutes. So actually we can do that in a high throughput fashion. And we can generate lots of data. We can get tens of thousands of data points. And we generated, I think, roughly 50 or 60K of those. And what having 60K of data points in hand allows us is to actually start using the power of deep learning. So what we did here, we started training a deep learning model on molecules, a graph neural network that we actually trained directly on the 2D molecular structure to predict those DFT computed excited state properties. And that actually worked pretty well. So we, across, I think, 10, 15 properties, what we get out is an R-square of like over 0.9. So with enough data, our molecule is clearly, or like our model is clearly able to learn how structure maps to excited state properties. Now, how does that help us? Well, if this is actually true, if the model learns how structure maps to excited state properties, then on the fly it should learn a representation of how the excited state of the molecules looks like. And this representation, if we try to use that now, the representation that was trained on the computed properties, and try to use that as a representation to actually predict the experimental properties, we actually start seeing a pretty significant boost in prediction performance. So what we do here effectively is transfer learning. So we pre-train our model to predict excited state properties from computation and use the knowledge that the model has learned to actually predict properties in the experiment. And now if we actually look at the same plot from before, so the left-hand side plot is the one that I showed you a couple of minutes ago. The right-hand side plot is the same, but this time not with the structural distance between molecules on the x-axis, but with the learned distance in the graph neural network embedding space. And if we try to correlate the distance in the embedding space, so kind of how similar are the two excited states, then we start seeing a correlation with how similar do the two molecules perform. Not perfect, it's definitely not a straight line, but it's something that, for example, our Gaussian process could start working with. And in fact, that's what it did. And that's the reason why we see improved prediction performance. And nicely, as I said, a surrogate model needs not only to make good predictions, but also to predict good uncertainties. And in fact, what we see is that the models that are trained on the physically meaningful embeddings also give predictions with better uncertainty calibration. So all of that is pretty promising. And actually gives us the opportunity to put the pieces together now. So what we did now is we effectively had our different labs all across the globe that could do experiments here. So what we set up is a cloud database that actually contains a pool of recommended experiments, and then a database of experiments that are ongoing, of experiments that are complete, and of all the building blocks that are available. And at every point in time, from the complete experiments, we now train one of those Bayesian machine learning models, actually condition it on all ongoing experiments so that the model also knows kind of which experiments are currently running somewhere. And then from the building blocks that are at that point in time available in all labs, we enumerate the active space, so all the compounds that are currently synthesizable. From that, feed them through a surrogate, get a posterior, decide on which experiments are the most informative to do next, and put them in a pool of currently recommended experiments. And whenever a robot in any of the labs that I showed you is available, it queries the experiments from the pool, starts running them. They're automatically matched and ongoing. If a second lab at some point wants to do another experiment, it can also query that, run it. It's also updated and ongoing. Completed experiments are fed back to the database. And at any point where any of those catalogs here change, the pool of experiments, the ongoing experiments, the complete experiment, this workflow runs again, so that this pool really gives us like a real-time list of which are the most informative next experiments to do. Now, so much about the toolbox. What I said earlier is prediction tools are nice, model tools are nice, but if they don't work in the lab, they're useless. And that's still the philosophy that I believe in. So what I want to show you on the effectively last content slide for today is how did it actually perform in a real life lab setting. What you see on this plot is the cumulative number of materials that we know with emission gain cross sections above certain thresholds. And what we see here is like the number of experiments that we did. And up to experiment 500, where we just did the statistical sampling, like the kind of design of experiments like sampling from the space, we don't see any new discoveries at all. But at the point actually where the Bayesian optimizer kicks in, we start seeing a rapid increase in the number of molecules and the number of candidates that we discover. And actually, we were kind of happy to see that some of the top candidates that we found in this discovery campaign could actually be scaled up. I don't want to go into the details here, but kudos to Jason Hines' team, who did really a fantastic job on doing all the scale up and developing the purification and processing for that. And those could actually be translated into the thin film and led to what I think is these days, in terms of small molecule emitters, one of the best, or like actually the best in terms of thin film amplified spontaneous emission threshold. So in that sense, we were very happy to see that actually the effort paid off and that the machine learning model we pre-trained on the computational data, then fine-tuned on the experimental data, actually made a pretty good decision-making algorithm for planning experiments in real life and helped us discover a bunch of new materials. And that kind of brings me to my most important takeaway message for today, that most of the AI co-pilots, machine learning models that we need for experiment planning and chemistry these days, we can't just train on the experimental data that's available, simply because we don't have enough of that. At the one that we have, yeah, well, don't get me started. But what we need effectively for efficient decision making is we need both data and expert knowledge. In our case, the expert knowledge meant telling the algorithm what excited states looks like, teaching it that, and making it make more efficient decisions here. And yeah, that's kind of a philosophy that I'm following with my lab, and where we kind of want to use Bayesian decision making and Bayesian machine learning in general as like very widespread tools for synthetic chemistry, or for synthetic chemistry labs in general, not only for materials discovery, but also, for example, for reaction optimization, for parameter optimization on instruments. Well, at some point when I talked to my undergrad, he said, like, is there anything else you can do than Bayesian decision making? Or in other words, like, if all you have a hammer, everything looks like a nail. Well, who knows? But probably Bayesian decision making is not Maslow's hammer that can be applied to any problem in chemistry. But I think in the world of chemistry, there are still very many nails around. And that's what our philosophy for the next years is, finding those nails and developing the right hammers to actually find more efficient decision-making tools in the chemistry lab. Yeah, I think with that, my time is over. So thank you very much for listening.